Okay, thank you. So first of all, I'd like to thank Blaise and all the organizers for putting up such a nice workshop and for giving me the opportunity to present this work, which appeared last week on Archive. And this is a project that was born from discussions between the string theory group in Würzburg, to which I belong, and led by Johanna F. and the condensed matter group led by Giorgio Sangiovanni in Würzburg. And let me mention the PhD student who was committed to this project, Thomas Kruger, who probably will apply for postdocs soon. And this is the outline of my talk. I will start with some basic introduction and some motivation. Then I will present a semi-holographic model, paying particular attention to what I will call Paul Zero's duality. And in the last part, I will present some numerical results. Okay, so we can start. So here, it's almost offensive for this audience to explain this, but let me take the risk and ask what are Mott insulators. So these are systems in which electrons get localized, so they don't conduct, due to strong Coulomb interactions, even in cases in which, from band theory, one would expect a metallic behavior. So we can have half field bands and still no conduction. These are an effect coming from strong interactions and not from, in general, from some long range order. And we know that in nature there are several systems showing such a behavior, like metal oxides and compounds of rates. So probably the simplest and still very rich model in which we can observe such a phenomenon is the well-known Hubbard model. In this model, we consider electrons on a lattice, and we consider an Hamiltonian of this kind with two terms: the term with parameter T, which is the kinetic term describing conduction, so hopping between two neighbor sites. And then we have a second term with this parameter U that predicts an energy cost whenever two electrons try to go on the same site, one with spin up and one with spin down. So if we consider the situation as half filling, we have one electron per site. If we take the limit in which U over T is larger, we see that it's energetically disfavored to have conduction, since the second term would forbid hopping between sites. And so in this model, we see a kind of transition between a metallic behavior and a Mott insulating behavior. And again, let me stress that this is an effect due to strong interactions. For this talk, it is particularly important to talk about Green's functions. So I will consider theories in 2+1 dimensions featuring a Dirac fermion, and this is my definition, but not mine, the definition of retarded Green function. So in an interacting system, one can write, in general, the Green function as the sum of two terms, the free contribution G0 and the self-energy contributions. And I will be interested in two features of this Green function. One is pulse, and pulse, as we know, signal excitations, so propagating degrees of freedom. And these are shown in metallic phases. So we have a Fermi surface. But so the self-energy can also diverge in some points. And when this happens, the Green function shows zeros. Now, in the past, zeros were not on the same ground of poles, but here I listed some papers from the condensed matter literature to show that the community got really interested in zeros, as they are now considered the hallmark of Mottness. Okay, so I already said several times that Mottness is a strongly coupled effect. And as we learned also from the nice review this morning, holography is a powerful tool to study such a systems. Indeed, from a quantum field theory point of view, since we want to describe a strongly coupled theory, we cannot use perturbation theories, and we need non-perturbative methods. So holography, as we saw, provides such a tool. But in fact, in pure holography, let's say, usually we describe the dynamics of composite operators. And in general, these composite operators do not satisfy single particle sum rules, meaning if we take the integral over the frequencies of the spectral density, in general, we will not get one for this composite operator. This can be seen, for instance, from one of the equations that Aristotle showed today. And this makes a comparison of holography with the conventional condensed matter systems a bit difficult, and even the discussions between our two groups, our condensed matter colleagues. And to circumvent this problem, one can use actually what is called semi-holography. So what I want to advertise in some sense is the powerfulness of the semi-holographic approach to describe Mott insulators. So we will use holography, but still have single particle sum rules. Okay, this leads me to the second point of the presentation. So let me say first in general what is semi-holography. So the idea of semi-holography was presented by Falkner and Polchinski several years ago. And the idea is to study in a quantum field theory framework the dynamics of some fields. In my case, it will be a fundamental fermion chi, coupled to a strongly coupled sector, and in particular to a composite operator of the strongly coupled sector. So the action of the complete system will feature a Dirac action for the fundamental field chi. Here I'm also including a gauge field since I will consider finite density states. Then in general, we will have a strongly coupled sector with its action and a linear coupling between the composite operator O and the fundamental operator chi. The strongly coupled sector in semi-holography is described by a holographic theory, indeed. So in general, these, as we saw from the review, these are large N strongly coupled theories. And the simplification that the large N limit brings is that the correlators of the strongly coupled sector factorize. So in particular, the most important object becomes the two-point function of the composite operator O. And in this framework, one can compute the retarded green function of the fundamental field chi. And in general, one can show that this will take this form where we have a free term, let's say, and then a self-energy. And in this semi-holographic approach, the self-energy is precisely given, it's given by the two-point function of the composite operator with some gamma matrices due to the spinor structure. So as I said before, with this approach, we have two advantages. We can use ADS CFT tools to compute the self-energy, but at the same time, we still have a field chi satisfying a single particle sum rules. So let me focus now on the strongly coupled sector, so the one that is holographic. And as we saw from the previous talks, this means that we can actually describe the theory using a gravitational theory with one dimension more. So I will consider a bottom-up approach in which actually the strongly coupled sector has two subsectors. One is the gluonic subsector described by the first three terms in the action. So we have just an Einstein-Hilbert term with a negative cosmological constant and a Maxwell term since I'm describing finite density states. And then we have another subsector, which is the fermionic one, featuring n degrees of freedom as opposed to n squared of the gluon sector. And this is just a fermionic operator psi, which is dual in the holographic sense to the composite operator O. Now, since this sector is 1 over n suppressed compared to the gluonic sector, I'm allowed to take the limit or the approximation where I neglect the back reaction of the Fermi on the geometry. And as a result, the background, I can study the fermion in a background given by the IDS Reissner-Nordstrom geometry. We also saw in the previous talks, it's not very important to focus on the details. Let me just say that I will always work in the zero temperature case. So the physics of Mott comes from the fermionic sector, actually. So this sector is given by the Dirac action plus a non-minimal coupling. Now, the proposal of using non-minimal couplings was put forth already 15 years ago by Ederatli, Phillips, and these papers. And actually, in these works, another non-minimal coupling was used, in particular the Pauli coupling, the dipole-like coupling. And it was argued that since one has spectral wave transfer, there should be the opening of a gap. Then actually this approach was a bit criticized in the literature, since it was thought that this was not actually a true gap. And the problem was reconsidered recently by the Korean group of SIM, and in particular this paper in which it was proposed another non-minimal coupling, a scalar non-minimal coupling, which is actually the one that we used. And it was argued that this should give rise to a harder gap. And also it was argued that it's closer in spirit to the U coupling term of the Hubbard Hamiltonian. But let me say that we're using this coupling and embed it in a semi-holographic context. So we will see, well, we have this dimensionless parameter eta, and as we will see, positive values of eta correspond to a semi-holographic metallic phase, while negative values to a phase that I will try to convince you it's a hot insulating phase. And this behavior comes from what is called the Paul-Zero's duality of the equation of motion, which is a correspondence between poles at positive value of eta and zeros at negative values of eta, and vice versa. So if we switch the sign of eta, poles get mapped to zero, and vice versa. So I think it's not that's important to see the derivation in detail. So actually the derivation for the dipole coupling was done several years ago by also collaborators. Here we generalized it for the non-minimal coupling. And the general idea is to write the Dirac equations in a somewhat clever ways, using some tricks, especially using rotational invariance to align the momentum in one direction, and then also choosing a clever basis for the Dirac matrix, such that the equation of motion, when we use this representation for the spinor in which we have two components, C plus and C minus, the relation of the equation of motion is of this kind, and in particular with a matrix S with only off diagonal elements. So the up component of C plus is only coupled to the down component of C minus and vice versa. Now, without entering into the details, using the holographic version of linear response theory, one can show that the two-point function of the composite operator is given by a limit of this function S plus and S minus. And in particular, plugging these answers for the equation of motion, one rewrites the equations of motion as two flow equations. And this is actually the equation that we have to solve numerically to find the results, together with infalling, what are called infalling boundary conditions. But what is important for our discussion is that if one looks at this equation, one can see even by eye that if we send S plus minus to its inverse, and at the same time we switch the sign of the momentum and the coupling eta, the green function of the composite operator essentially becomes its inverse. And because of this, this is a very powerful, well, a very strong relation. And in particular from this, we see that poles at plus eta correspond to zeros at minus eta.
Sorry, so this remains true also at zero eta, right? I mean, then you just invert k.
Yes. And at eta equal to 0, the determinant of the green function should be 1.
So does that have to do with the alternative quantization? Yes. Okay, yeah, yes, so that's it.
Yes, indeed. As I didn't mention because it's a bit technical, but here we are in the m equal to 0 case. So if m smaller than 1/2, one can actually study the theory in two versions called standard and alternative quantization. And at n equal to 0, actually the two theories are the same. But what is important is that if you switch quantization, the non-minimal coupling is odd under this switching. So essentially, changing the sign of eta is completely equivalent to switch quantizations. So thanks for the comment. Okay, so we have this Paul-Zeros duality for the composite green function that I recall in our setup, in the semi-holographic setup, is the self-energy. And actually, since the self-energy comes from a strongly capped sector with a large number of degrees of freedom, one can see, and we will see it in a moment, that the exact Paul-Zeros duality of the self-energy gets inherited as an approximate Paul-Zeros duality at small momenta and frequencies by the green function of the fundamental operator. And this kind of duality is close in spirit to what one observes in mathematical solutions of the Hubbard modeling condensed matter systems. And the plus of this approach is that one can actually give an interpretation of the divergences of the self-energy, and so the zeros of the green function 0, because the self-energy diverges whenever we have excitation of the composite operator, so collective excitation of the strongly coupled sector.
So do I understand correctly that since you're working at zero temperature throughout, then the zeros that you inherit, they're the zeros of the Green's function of the fermion in the critical infrared geometry of your radiation motion black hole.
Yes.
Is that right?
And okay, so I want to conclude showing some numerical results. Well, this is a kind of from the numerical point of view, trivial result because this is the pole-zero duality of the self-energy, and we showed exactly analytically, so we don't need to actually check it numerically, but I show it because this is the kind of plot that I will show in a moment for the fundamental fermion Green function. So here we see precisely that we have an exact correspondence between peaks that are poles and zeros that are peaks pointing downwards when we switch the sign of eta, and here I'm at k equal to 0. But as I said, this exact pole-zero duality becomes an approximate pole-zero duality for the fundamental fermion Green function. And this can be seen by these density plots. Here I'm plotting the logarithm of the absolute value of the determinant. So we see on the left positive value of eta, which, as I said before, it's a semi-holographic metallic phase. And we see the bright spots, the bright lines are divergences, so poles. So we see on the left a relativistic dispersion relation with speed of light that is smaller than 1, of course. And we see that when we switch the sign of eta, the poles become 0. This is quite precise for what concerns the crossing diagonals. And then we see a good approximation also for the for what are on the right the upper bands. Now I haven't mentioned this. These plots are realized, I obtained for a value of the parameter that should scale out as n equal to 10. And of course, the approximation gets better and better if you increase the value of n. So already at a relatively small value of n, the approximation seems pretty good. And here I take a section at k equal to 0. So we see that at negative value of eta, we have a 0 inside the gap, which is, as I said, a hallmark of Mott physics. And this gets mapped with a pretty good approximation to the poles when we switch the value of eta. Here I have several plots in which I increase the absolute value of eta in the negative region. So what I want to say that it's a Mott phase. So eta equal to 0, well, this is still not a Mott phase. We have a quite broad peak, but as we see, as soon as we switch on eta, we have the formation of a gap. Well, from the plot top right is not still very clear, but from these two plots, we see that we have a 0 inside the gap. The two vertical lines denote the endpoints of the gap. Well, I haven't said the red curve is the imaginary part, thanks. And the blue line is the real part. And in my conventions, the imaginary part should be positive. Usually, people is used to use the other sign. So the model is well behaved. Here, I'm plotting the value of the gap as I increase, or if you want, decrease eta. So the gap opens, depending on the criterion that one uses, at a very small value of eta. Here I'm putting error bars, since there is always an ambiguity in defining what is a gap. This plot is obtained by considering the value of the spectral density at k equal to 0. And so we are taking two criterion, one in which I ask the spectral density to be smaller than 10 to the minus 2, and the other one in which I take E to be smaller than 10 to the minus 5. And as I increase eta, the two values converge because the peaks of the valence and conduction band of the upper band get sharper and sharper. And then here I'm plotting what happens when we increase eta in the positive region. So at eta equal to 0, we have this plot on top left with a broad peak. And as we increase eta, these peaks get sharper and sharper. But we see that we always have a Fermi surface. We always have a peak close to the chemical potential. And
sorry, what's the peak close to the chemical potential?
Sorry?
With these plots.
Well, we have a pole.
Okay.
We have a close to the chemical potential.
Then it looks like you have a secondary peak.
Sorry?
It looks like there is a secondary peak.
Yes, as one increases the value of eta, there is a spectral transfer to other peaks that we interpret as conduction and valence bands. So this is not actually, we refrain from calling it a normal metallic phase, and this is why we are calling semi-holographic metallic phase. Also because for eta equals to 5, if one considers the residue of the close to the chemical potential, one finds a value which is 0.5. So whether to call this coherent metal or not, I don't know. So our interest was mostly in the Mott phase. For this phase, we just remark that we have a Fermi surface, let's say. Okay, so this brings me to the conclusion. So what I tried to show you is that semi-holography can provide a good approach to study Mott physics. We saw that from the exact Pole-Zero duality of the self-energy, the Green function of the fundamental fermion gets an approximate Pole-Zero duality, and this allows us to interpret the model as a model displaying a Mott phase. And then, okay, I showed some numerical results corroborating this interpretation. For the future, okay, one can consider, of course, what happens at finite temperature. I didn't mention before, but this the coupling that you use, the non-minimal scalar coupling, is not the only one that is supposed to give a good gap. In the Korean group proposed even other couplings, so one can study also these couplings. And also, in the papers that I listed, at some point, the zeros were shown from the condensed matter community to also give rise to interesting topological properties. And so it would be interesting also to see if we can include these aspects in our approach. And if anybody in the audience has other suggestions, they are welcome. With this, I conclude. Thank you very much.
Question for Alessio.
Yeah, like a question, like, so what do you learn more about Mott insulators, like using this approach in comparison to just, some complicated, DFT kind of things, other methods to describe Mott insulators?
Yes. So other approach are like, I don't have a full vision of the other approaches, but usually when one studies the Hubbard model, one finds the transition accompanied by thermodynamic phase transitions. And what is appealing of these models is that it's not clear, a priori, we are not having a thermodynamic phase transition. So this switch of behavior is entirely due to this switching of quantization, as it was mentioned before. So it's a kind of another perspective in this sense. And also from other approaches, it's not, that I know, it's not entirely clear how to interpret the divergences of the self-energy. While in this approach, they are precisely given by collective excitations of this strongly coupled set. Whether this is satisfying to advertise their semi-holographic approach or not depends a bit on. But this is my perspective, let's say.
Right, I think it's time for lunch. Let's thank Alessio again. There'll be 2 more talks this afternoon at 2 o'clock.